Welcome back to this YouTube channel for practice problems for actuarial exams. We'll look at a problem from exam MLC today. It's a longer written answer problem. Let me just remind you of the links for various sites that I have. I have adjusted some of them, so I'll consistently use the BTDT acronym that stands for Been There, Done That. I use it because I want you to understand that when you take the actuarial exams, during the exam you have so little time that you cannot count on figuring it out and thinking your way out of trouble and so on. On written answer exams, you generally must have very clear idea of what you're doing and be almost done in about 3 minutes, because you have 5 to 6 minutes per problem. So if you don't know what to do after 3 minutes in a multiple choice problem, you should just go to the next problem, leave this one, come back maybe later and guess, but do not spend time unnecessarily. Try to stick to the amount of time you have per problem. And because of that, you have to be so prepared that when you look at a problem on the test, you can say, been there, done that. You have done a problem like this, you know what to do, you can immediately start doing it. If you are not able to do this, that means you haven't yet prepared for the exam. Prepare for the exam seriously, so that you will have done hundreds and hundreds of problems, and do difficult problems. Don't do just easy problems, because that will not get you ready for that shock of the test. You need to get shocked before the test. Do hard problems. This is very important. You need to practice really hard so that on the day of the exam you know what to do immediately. Here's our problem for today. It's a written answer section in spring 2015 exam MLC, problem number 3, and I will post a video of this in my YouTube channel. We have a life insurance company that issues a whole life annuity immediate with annual payments. The annuity is issued to a 65-year-old. The annuity pays $50,000 at the end of each year for the life of the annuitant, with the first payment being made at age 66, at the end of the year, so that's when the person turns 66. First payment, of course. A single premium is paid to purchase this annuity. You are given that mortality follows the illustrative life table. The interest rate is 6%. An expense of $100 is incurred to make each annuity payment. Issue expense incurred at issue is $3,000 per policy. Commissions are 10% of the single premium. Part A says, assume that the single premium G is 110% and 10% of the expected present value at issue of benefits and expenses. Show that G is 555,000 to the nearest 5,000. You should calculate G to the nearest 100. Part B, using G from Part A, calculate the probability that this policy will generate a profit. Another life insurance company issued 8,000 independent annuities identical to that described above. This company determines the single gross premium per policy, G upper P, using the portfolio percentile premium principle, such that the probability that the present value of the loss at issue on the portfolio is negative is 90%, which simply means that the company has a profit. Negative loss is a profit, with probability 90%. Show that GP is 500,000 to the nearest 10,000. You should calculate G upper P to the nearest 100. In Part D, GP is calculated so that the portfolio of annuities has a 90% chance of generating a profit. G is such that the probability of an individual policy having a profit is less than 90%. Explain why G P is less than G. So here's part A of the solution. An important thing to note immediately is every time on the exam you see the words illustrative life table, check immediately if the interest rate that is given is 6%, because that's the interest rate used in the illustrative life table, and that means that if the interest rate is 6%, you can use all the annuity and life insurance single benefit premiums that are given in the table. And if the interest rate is not 6%, then you can only use the mortality data. All the other data is calculated assuming that the interest rate is 6%. Since the single gross premium is 110% of the expected present value at issue of benefits and expenses, it is equal to 1.1 times expected present value of benefits and expenses. So 50,000 life annuity at the end of the year starting at age 65. So life annuity immediate starting at age 65, which means that the first payment is really at age 66, and expenses of 100 every year paid at the same time. The $3,000 expense plus 10% of premium. And this is an equation in which G is the unknown, and there are certain numbers there that we need to, certain values of annuities that we need to figure out. But A65 is equal to A double dot 65 minus 1, and A double dot is given in the illustrative life table. So we simply solve this as an equation for G, and then look up A double dot 65. It is equal to 9.8969. Plug it in, and we have the answer. This answer is 555,000 to the nearest 5,000. Calculated to the nearest 100, it equals 554,600. In part B, we're supposed to use the gross premium from part A and calculate the probability that this policy will generate a profit. So we want to find the probability that this company makes money on this product. And the company gets the premium G, and it pays out the amounts that you see in the first line in parentheses, and those amounts are random. That's not a fixed amount like G. G is just a number, but these amounts are random because they depend on how long the insured will live. The company pays life annuity immediate, so payable at the end of the year. And one very important observation is that if the person dies during the year, then there is no payment at the end of the year. So it's a life annuity immediate A angle K of the benefits of 50,000, and then also life annuity immediate of expenses of 100. Then the $3,000 expense and 10% of premium expense. So all this is paid out, the premium G is collected, and the difference of the two is how much money the company makes. That is a Wren variable, depending on K, the number of whole years lived by the person, insured, by the insured. So we want the probability that this expression is greater than 0. And we combine the like terms. G minus 0.1 G is 0.9 G. 50,000 plus 100 is 50,100 A angle K minus 3,000. Then we write A angle K as 1 minus V to the K over I, the standard formula for present value of annuity immediate. But we can just write that V thing is 1.06 to the negative 1. So V to the K is 1.06 to the minus K. Okay, then we also plug in what G is, and G is 5,054,615.91. So multiplied by 0.9. So do all the multiplications there. We get 49 496,154.32 minus 50,100 over 0.06 plus 50,000 over 0.06 times 1.06 minus k, this to be greater than 0. The negative 3,000 is already incorporated in this calculation by being subtracted from 0.9 times 554,615.91. Then, after we calculate the 50,100 over 0.06, subtracted, we get a negative number actually. Negative 338,845.68 times 50,100 over 0.06 times 1.06 to a minus k. And now what we do is we move the negative 338,000 and some to the right hand side, and then divide both sides by the number that is in front of 1.06 or minus k. And then all these numbers are on the right hand side. We calculate that and we get the probability that 1.06 to minus k is greater than 0.4058032. And then one very important rule that you need to remember is that when the unknown is in the exponent and you're solving an equation or inequality, take the natural logarithm of both sides. So we do that. Then, because the natural logarithm of, say, a to the power b is just b times natural logarithm of a, natural logarithm of 1.06 to a minus k is equal to minus k times the natural logarithm of 1.06. And so we get the inequality that we want the probability of this inequality being true, where it's minus k times L natural logarithm of 1.06 being greater than natural logarithm of 0.4058032. Now we divide both sides by minus the natural logarithm of 1.06. Now notice this, the natural logarithm of the fraction on the right hand side, that's actually a negative number because the number is less than 1. The natural logarithm of 1.06 is positive. But with a minus sign in front of it, it becomes negative. We're dividing both sides by minus natural logarithm of 1.06, so by a negative number. When you divide an inequality by a negative number, you switch the direction of inequality. So this becomes the probability that k is less than minus ln of 0.4058032 over ln of 1.06. Well, we just calculate the ratio of these natural logarithms, put a minus sign, so it's a negative number divided by a positive number with a minus sign in front, so it becomes positive. It is probability that k is less than 15.478013. But in terms of whole numbers, that's the same as saying that k is less than or equal to 15, which means that that's the probability that number of whole years lived is 15 or less, right? That means that by the time the 16th year arrives, the person is dead. So this is the probability that the person is dead during the first 16 years, because the person does not live full 16 years. K less than or equal to 15 means that the number of full whole years lived is 15 or less, so the person is not alive for full 16 years, dies before that. That means that that's 16Q65. The person was 65, if you recall from the problem. That's the same as 1 minus 16P65, and 16P65 is just L81 over L65, which we have in the table. We just look up those numbers. So this ILT symbol under the equality means that I'm plugging in the numbers from the illustrative life table. And there is our answer. The probability is approximately 0.52215885. In part C, we have 8,000 annuities independent of each other. Because of such large number of independent annuities, we can approximate probabilities of sums of independent identically distributed random variables, describing them with a normal random variable of the same mean and variance as such a sum, based on the central limit theorem. And one very fundamental principle about approximation with the central limit theorem is this. You always approximate a sum of independent, identically distributed random variables. That's the core principles. That's what you need to approximate. It has to be a large number of them. So I would say at least 30. The more the merrier. 8,000, there's no doubt that, yes, we can do that. And then the key insight is what I call the fake ID principle. If you have a fake ID, you still need to put a real picture on it. Otherwise, it's not going to work. Well, why do young people get fake IDs? To buy alcohol. So you go and buy alcohol, you whip out your ID, show it, and if it has a picture of somebody, let's say, with gray hair that looks completely different than you, then that person is allowed to buy alcohol, but that person is not you. So it's not your ID. But if the picture is you, and you're breaking the law, you shouldn't be doing this, but if the picture on the fake ID is you, it is possible that the fake ID will work. I'm not telling you to do that, you shouldn't. And probably most of you already are of legal drinking age anyway. But the principle is the same. The normal distribution that we're using for the approximation of a sum of independent identically distributed random variables is a fake distribution. It's not the real distribution that we're approximating, but it's close enough. It's good enough for the estimates of probability. But if you think about this fake thing working, then, well, it must have the same picture. So what's a picture here? Well, it's some kind of core characteristics of the distribution. So those two characteristics that are core and fully describe a normal distribution are what? A normal distribution is fully described by its mean and variance. Once you know the mean and variance of normal distribution, you know it completely. Therefore, the normal distribution that you're using for the approximation of whatever sum of independent identically distributed random variables you're approximating, that normal distribution must have the same mean and variance as that sum. That's what I call the fake ID principle. Okay? So the random loss at issue for a single policy is the benefit, present value of benefits plus present value of expenses minus the premium. So we combine the like terms and we get this expression that you see here. What is the expected value of this random loss? Well, it's the expected value of what we just calculated. So the expected value of angle K, we already noticed this, that it can be calculated as a double dot angle K minus 1, and then the expected value of that is a double dot 65 minus 1. And then the rest is just straight calculations, except that we still have this 0.9 GP left in the calculation, because we're going to figure out that premium from the approximation. So what about the variance? Well, the variance is the variance of the same random variable. And in that calculation of the variance, we notice immediately that 3000 minus 0.9 GP, that's a constant. So it doesn't have any variance. We disregard that. So it's only the variance of 50,100 A angle K. That's 50,100 squared times variance of A angle K. And A angle K is 1 minus V to the K over 0.06. And then we divide the top and the bottom by 1.06 to get 1.06 to the minus K plus 1. And then all the constant terms don't have variance, so we ignore them. All the numbers we get put together, but the crucial question is, what is the variance of 1.06 to the minus k plus 1. Why in the world did I go from v to the k to v to the k plus 1? Because v to the k plus 1 is the present value of a death benefit for a discrete whole life insurance. And its variance is known to be 2a65 minus a65 squared. And those numbers are in the illustrative life table. We looked them up, plugged them in, and there is our answer. It's a very large number, but that's to be expected. And then we take the square root of it to get the standard deviation. Now, for 8,000 such policies, the loss at issue is 8,000 times the loss random variable whose parameters we were just calculating. And since they are independent and identically distributed, 8,000 L is approximately normal with mean equal to 8,000 times the mean of individual policy, and standard deviation equal to square root of 8,000 because the variances are added, so 8,000 times individual variance, and the standard deviation will be square root of 8,000 times individual standard deviation. So if we want 0.9 to be the probability that 8,000 L is less than 0, then that's the same as 8,000 L minus its mean divided by standard deviation being less than 0. And so the probability of this being less than 0 minus, we subtract the same thing and divide by the same thing on the right-hand side. Initially, we just had 8,000 L less than 0. We do the same thing to 8,000 L on the left-hand side and on the right-hand side to 0. So 0 minus 8,000 times the expected value divided by standard deviation. And this becomes the probability that z is less than this entire expression with 0.9 GP in it. GP is in it. Okay, this z is the standard normal random variable that replaces the left-hand side, because the left-hand side, we say 8,000 L is approximately normal, then 8,000 L minus its mean divided by its standard deviation is approximately standard normal. And what's the probability that z is less than something? Well, that's the cumulative distribution function of standard normal value. And we want that number, z being less than that number, whatever this whole expression here we have on the right-hand side, to be such that this is 0.9. In other words, we want to find the 90th percentile of the standard normal distribution. The number that is on the right-hand side of inequality z less than the whole expression there, that has to be the 90th percentile of the standard normal distribution. Well, we know the 90th percentile of a standard normal random variable is 1.282, so this expression has to be 1.282. Now this becomes an equation in which GP is unknown. We solve for GP, and we get 495,684.54. This is 500,000 to the nearest 10,000, and 495,700 to the nearest 100. Variance per policy of a single policy loss at issue is much larger than variance per policy for 8,000 policies, and this makes a portfolio of 8,000 policies significantly more predictable. Now, this is possible. We're answering part D about the comparison of the variances. This is possible. This is the case because these 8,000 policies are independent, identically distributed. And when you add up things that are independent, identically distributed, when you have a lot of them, they become closer and closer to normal distribution, and they become more predictable. Since we are using a percentile premium, this means that the 90th percentile of the distribution of the loss at issue per policy will be much larger for a single policy. And it's per single policy that we're looking at here. Furthermore, for a single policy, we cannot use a normality assumption, and that makes predictability even worse because we would have to actually know the exact structure of the distribution of the losses for that specific policy. While for a sum of them, we approximate the sum with a normal distribution. And this is why G is more than G P or GP is less than G. We'll actually calculate the premium G that makes a probability that a single policy generates a profit as 0.9, although this was not expected on the exam. So we must have the same inequality as before, 0.9 equal to the probability of premium minus expenses being greater than 0, and we do the same trick with writing A angle K as 1 minus V to the K over I. And again, we solve everything, and we get this expression, the probability that K is less than the expression on the right-hand side, and that's equal to 0.9. So we're looking for the number K.90, such that the probability that K is less than K.90 is 0.90. It's 90th percentile. And we're going to do this using the illustrative life table because it tells us about the probability of living to various ages. Now, this K.90 being a 90th percentile is the same as probability of K being greater than or equal to 0.90 being 0.10. So we're looking for a time such that surviving to this time in terms of policy duration, and for survival to that policy duration or age 65 plus the time of the policy, duration of the policy. So for X being that, the probability of survival to age X is 0.10, or LX is 0.10 times L65. So 65 is the age of the person when the person got the policy. And L65 is given in the table as 7,533,964, and we're looking for the age where we have 1/10 of that. That's 753,396.40. And the population reaches that size between ages 91 and 92, so that we know that probability for a 65-year-old of survival 26 years is more than 0.10 and 27 years is less than 0.10. But that's the same as saying that the probability that K is less than or equal to 25, because T less than or equal to 26 is the same as probability that T is less than 26 because T is continuous, but that's being less than 26 is equal to a probability that K is less than or equal to 25. And that's less than 0.90. So survival, the number of whole years lived, being 25 has a probability that is less than 0.90, but 26 has a probability of being more than 0.90. Also, probability that K is less than or equal to 25 is the same as probability that K is less than 26. So that's that probability that K is less than 26 is less than 0.90, while the probability of K being less than 27, which is the same as probability that K is less than or equal to 26, is more than 0.90. And remember that we're looking for a number such that probability that K is less than K.90 is 0.90, and we need it to be a whole number, an integer. And 26 is too small, based on what we just said. So we take 27. It's too large, but it's the first integer that meets the condition. And then we set that to be at K.90, which has to be equal to what you see here on the left-hand side from our previous calculation, and from that we can calculate that premium. Now I should stress that this was not required on the exam. This is just an interesting exercise of carefully calculating how long a person should live so that you have this condition met. And of course we see that the premium that assures this condition is significantly greater than the premium assuring the same condition but for a portfolio of policies, as expected. Please remember that this is copyrighted material, and also old exam problems belong to the society that published the exam. Good luck in your studies and good luck on the exam.